In this video, we're going to try and find the eigenvalues of a 3 by 3 matrix. But firstly, we need to know what the eigenvalue is. So by definition, lambda is an eigenvalue of some matrix A if and only if A times some vector x equals lambda times the same vector, where x is a non-zero vector. Okay, now we can rearrange it to see that A times x minus lambda times the identity matrix times x equals the zero vector. We can just plug in the identity matrix because it doesn't really change anything, it's just 1. And if we take x out of the bracket, we have A minus lambda I times x equals the zero vector. Now we know that x is non-zero, so we need this bit to be equal to 0. Now in order for this matrix A minus lambda I to be equal to 0, we need it to be non-invertible, not invertible, and therefore we need its determinant to be equal to 0. Now having that, we can move on to our example and try and solve it. So you have our matrix A here. Now we need lambda times I, which is just the identity matrix with lambdas on the diagonal and zeros everywhere else. And now A minus lambda I is equal to minus 4 minus lambda. We have this minus this. It's minus 4 minus lambda. Now 0 minus 0. And again 0 minus 0. And again. Then we have minus 2. I'm going to use a different color for that. Minus 2 minus lambda. And use this here. And then minus 3 minus 0 is just minus 3, then again 0. We have minus 3 minus 0 is minus 3. And then minus 2 minus lambda goes here. Now we need to find the determinant of it. So determinant of A minus lambda I equals to, we can rewrite the first two columns on the right hand side. That will help us with finding the determinant. It's here 0 minus 2 minus lambda, then 0 and minus 3. It's just going to help us with finding the eigenvalues. So firstly we need this diagonal, so that's minus 4 minus lambda times minus 2 minus lambda squared, because we have it twice. Then we have 0 minus 3. Oh, we're going to see it here better. That's 0 minus 3 and 0, which is just 0. And then 0, 0 and minus 3, which is again 0. Then we're going to subtract. So firstly we have this, which is 0 times minus 2 minus lambda times 0, which is just 0. Then we have minus 4 minus lambda times minus 3 times minus 3. It's minus 3 times minus 3 times minus 4 minus lambda. And then we have 0, 0 and minus 2 minus lambda, which is just 0. Now if we simplify it, we have minus 4 minus lambda as the first one. Then we're going to multiply this out, which is 4 plus 4 lambda plus lambda squared. Then we have all the zeros, and then we have minus 9 times minus 4 minus lambda. And if we multiply that out again, that gives us minus 16 minus 4 lambda minus 16 lambda minus 4 lambda squared, and again minus 4 lambda squared, then minus lambda cubed plus 9 lambda plus 36. And in the end, it reduces to minus lambda cubed minus 8 lambda squared minus 11 lambda plus 20. And that is our characteristic polynomial. Now, as we said earlier, in order to get the lambdas that are actually our eigenvalues, we need the characteristic polynomial to be equal to 0. So that we need to find the roots of it. We're going to rewrite it here. Minus lambda cubed minus 8 lambda squared minus 11 lambda plus 20 equals 0. Now there is this very nice method of finding our roots. So we're going to just write down the coefficients of the polynomial. So we have minus 1, minus 8, minus 11, and 20. And we're going to make this little table here. And we can try out some roots that we think may be valid. I'm going to try with minus 4, which we know is a root. And we just rewrite this minus 1 here, and then minus 4 times minus 1 is 4, and then we subtract 8, and that gives us minus 4. Then again, we have minus 4 times minus 4, which is 16, and then minus 11, so 16. Plus minus 11, so 16 minus 11 is 5. Then we have minus 4 times 5 is minus 20, plus 20 is 0. And now we know that minus 4 is our root. So we can write lambda plus 4 times, and now we get our coefficients from this table. So minus 1 lambda squared minus 4 lambda plus 5, and that is equal to 0. Now we can solve that as just a quadratic equation. So our delta is 16 plus 20, which is just 36. So that lambda 1 will be 4 minus square root of delta, which is 6, over 2a, which is minus 2. And that gives us 1. And then our second lambda is 4 plus 6 over minus 2, which is minus 5. So now we have all of our roots, and we can write a characteristic polynomial in the form lambda plus 4 lambda minus 1 times lambda plus 5, and that equals to 0. And there we have our eigenvalues. So lambda 1 equals minus 4, lambda 2 equals 1, and lambda 3 equals minus 5. In the next video, we're going to try and find the eigenvectors corresponding to those eigenvalues. Thank you.